Hey everyone! Welcome to the lecture on gas laws. Before we begin, make sure you have your guided notes in front of you, and of course you're probably going to want a little calculator on the side. After all, this is honors chemistry. Let's begin. We are going to start with a review of something called the kinetic molecular theory of particle motion. So the kinetic theory makes certain assumptions, and for most of you, this will be a review. Some things to keep in mind in the kinetic theory is that gas particles are really, really small, and they move in very fast, random straight paths. Another assumption that we can make is that they bounce off of one another. Whenever they hit one another, they bounce off, and they also bounce off of the container that we put these gases in. Remember, gases have no definite volume and no definite shape, so they have to take the volume and shape of whatever container you put them in. Another assumption is that no energy is lost or gained when particles collide with the container or with one another. Another fact to keep in mind is that gases have a lot of empty space in between the particles, so gases are what we call compressible. This is a good thing, because we would never want to put anything inside of our airbags in our cars that wasn't compressible. In physics, kinetic energy is really another way of talking about energy in motion. Potential energy is another way of talking about stored energy. So here's something that I want you to remember. When gases are heated, the particles start to move faster. That means that they have more kinetic energy. Now, really, what are we saying? In chemistry, average kinetic energy, the amount of kinetic energy that any gas substance has, is directly related to whatever the temperature of that gas is. So in other words, when you take a temperature with a thermometer, you're making a relative measurement of the kinetic energy of the atoms or molecules that are moving around. Every time one of those particles collides with a thermometer, that energy is transferred to whatever liquid is inside of the thermometer, making that liquid expand, and the temperature inside of the thermometer will rise. In gas laws, we have certain variables that we have to keep track of. That's what I'm going to be teaching you. That's what this whole lecture is about, is gas laws. And here are the pressure variables. Anytime you see a capital P in any of the formulas, that is representing pressure. It has all these different units, and they're all interchangeable. One of the units that we use to measure pressure is something called kilopascals. You can take the kilo out and call it pascals if you want, but we traditionally use kilopascals in chemistry. Another unit of pressure is atmospheres. You'll see that the symbol for atmospheres is ATM, and this particular unit is very familiar to you because do you remember that 1 mole of gas at STP, standard temperature and pressure? Do you remember what standard pressure was? We called it 1 atmosphere. 1 atmosphere is the amount of atmospheric pressure that is exerted over your head at sea level. Well, another unit that we use for pressure is something else called millimeters of mercury, mmHg. mmHg can sometimes be called, another nickname that instead of saying millimeters of mercury, that's a mouthful, right? Instead of saying that, sometimes we say just simply torr. Torr is millimeters of mercury. Millimeters of mercury is torr. The next unit that you're going to commonly encounter in the gas laws is the unit of volume, a capital V. Anytime you find a capital V, you need to remember that the volume has to be represented in a very specific unit. Volume can only be expressed in liters. Liters only. The next unit that you see here is a capital T. That stands for temperature. Temperature must be measured in this special unit called kelvins, and kelvins has a symbol of a capital K. Don't worry, if you don't know what kelvins are, we'll get to that later on in this lecture. I'll show you how to get those. And the last unit is the only lowercase letter, is lowercase n, and that represents the number of moles. There are certain factors that affect gas pressure, and some of these are kind of, obvious to most of my students. So take this picture. You have a balloon and it's being inflated by, it looks like a bike tire pump. So what if I increase the number of gas particles that are inside of a container without changing the temperature of the gas particles in the container? In other words, we maintain the temperature so that temperature doesn't change. What do you think is going to happen to the pressure inside of the container? Yeah, see, most students know that the pressure would increase. So here's a picture. You start off with this diagram over here, and what I did is I counted. I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 particles. And if I add 10 particles and maintain the temperature doesn't change, basically what's going to happen is it's going to get more crowded inside of this container. Now, if it gets more crowded inside of the container, that just basically means that the particles are going to collide between each other and the container more often. You know what that means? More pressure. So you can assume that pressure is a direct correlation between how often the particles are colliding with the container or themselves. That's what we call pressure. Okay, so what you have in this diagram is a piston. Now a piston typically will have some kind of barrier in there, right here, that is actually able to move up and down. So if you can just kind of imagine yourself taking this handle here, and you can push it down so that the wall squeezes the volume down, or you can take that handle and pull out so that the volume increases inside. But the key is that none of these gas particles can leak out, and nothing from out over here can leak in. So a piston is kind of like an isolated area where the gas particles have to stay. So one of the things that I want to make sure you can visualize is that you can raise the pressure that is exerted by the gas particles inside of this little piston. Now, if you wanted to increase the pressure, what would you have to do to this handle? Would you decrease the volume, or would you pull it out and increase the volume that the gas particles are sitting in? So if you take the handle of this piston and you push down, you're literally going to decrease the amount of volume that all of these gas particles have to roam. That would be kind of like me making all 30 of my students fit, say, in a bathroom stall. Okay, if I decrease the amount of volume that you guys have to roam around, you're going to bump into each other more often, and you're going to bump into the container walls more often, which of course will naturally mean that you have an increase in pressure. The next situation I would like you to consider is anytime you increase or decrease the temperature of the gas particles inside. And this goes back to your kinetic molecular theory. So notice that the size, the volume of these two containers are the same. So I'm not changing volume right now, but you'll notice that I'm heating up the gas particles. And the kinetic molecular theory says that when you heat up gas particles, they're going to move faster. And if these guys are moving faster, they're going to collide with each other and collide with the container more often, which means, of course, you're going to increase your pressure. Now, let's put all of those concepts into specific laws for each of those relationships. The first law that I want to point out is Boyle's law. Boyle's law states that when pressure goes down on a container with a gas in it, the volume of the gas has to increase. So think about how we switched the volume inside of the piston. So if I were to pull the piston out and allow the gas to have more volume, that would naturally cause a decrease in pressure. Well, that's Boyle's law. So think about this relationship. When pressure goes up, that means that I squeeze the volume so that the volume was decreased. This relationship where one goes up and the other one goes down is called an inverse relationship. Well, what does an inverse relationship look like? So if I were to graph pressure versus volume, what would that relationship look like? Well, before we get there, let's make sure that you understand some specific formulas and how the formula works. So here I've got 3 different pictures of my piston, and you'll notice that they all represent different volumes. And I tried to draw a picture with the same number of little gas particles inside, but you get the basic idea here. So here is the law, the expression of the law written on top. Typically what we say is P1 times V1 is equal to P2 times V2. You don't usually need this P3, V3 or anything like that. Alright, so how does it work? Well, if you multiply pressure and volume and make sure your volume is always in liters, And make sure that these two pressures, whatever they are, that they're in the same units, because you can't talk apples and oranges. You have to make sure that the pressure units are consistent throughout the equation. So here's some examples down here. Let's see, 100 kilopascals times 1 liter would give you 100. So 100 times 1 is 100. Let's look at the second sample. The pressure has been decreased. You'll notice that the volume increased as a result. So this is 50 times 2. Well, 50 times 2 is still 100. Let's look at this last example. I really squeezed down the piston, and you notice that the pressure increased to 200. But notice that the volume is 0.5. Well, 200 times 0.5 is still going to give you 100. So you see how this law works? All of these different pictures represent different pressures and volumes. Okay, let's talk about when you graph it. What if I graph volume and pressure? So think about the relationship. Your volume should decrease as you increase the pressure. So if I squeeze down on the piston and I decrease the volume, that's going to cause pressure to increase dramatically. And so you're going to notice right here that here I am, I'm decreasing the volume of the piston, and here's pressure. Pressure is actually increasing. As I drop this down, you're getting more positive on your pressure. Now think about it in the reverse. If I lower the pressure, then the volume will steadily increase. Okay? This is what an inverse relationship looks like when you graph it. This is the same data. I know it doesn't look like that, but it's a straight line, you'll notice. But then look at what I did to my data on my pressure. This is what we call a reciprocal. Now, when you take the reciprocal of one of the values, I could have chose volume, I could have chose pressure. If you take the reciprocal of one of the variables, you'll end up with a straight line. So this is something to keep in mind when we talk a little bit more about inverse relationships. Here's a perfect example. So this is where you're going to want to pull out your calculator. So this is an example of Boyle's law. A birthday balloon contains 45.6 liters of helium at 125 kilopascals. What is the volume when the balloon rises in the atmosphere to a pressure of only 15 kilopascals? So sometimes it's good to visualize what you know and what you don't know. Okay, it looks like you started off with your balloon with this volume and this pressure. So we could call these two variables, we could call these your initial. Then read the question. What is the volume? So this is what we're trying to find. What is the volume when the balloon rises in the atmosphere to a pressure of only 15 kilopascals? This is the pressure on the other side. So the P1 and the V1 are your initial coming from up here. The P2 is this new pressure, 15 kilopascals. And here is what you have to solve for. So I'm going to divide P2 on both sides. And so you'll notice that on this side the P2 canceled, but on here we're going to stick P2 on the denominator. This is how I would solve this problem. So grab your calculator. I want you to plug in these units and solve. The next relationship that I want to bring to your attention is the temperature-volume relationship. So think about this. When you heat up a gas, the volume should naturally change. This is known as Charles's law. So under constant pressure, that's the key, when temperature goes up, your volume is going to go up. And when temperature goes down, your volume is also going to go down. So think about if I take a balloon and I throw it in the freezer. That's going to make the gas particles inside of the balloon start to move slower, and they're going to exert less pressure on the outside of the balloon. This is known as a direct relationship. A direct relationship, you'll notice, volume here, temperature down here, has a perfectly straight line. So I would like to challenge you to think about what would happen if back in the time that Charles was doing this experiment, what would happen if he continued to lower and lower and lower the temperature of the gas? Notice where it creeps to right here? Come across. that would mean it has absolutely zero volume? What is this temperature thing all about? Wait a minute. This must have a really important factor in chemistry. At least I hope you realize that. In fact, it's impossible for gases to not have a little bit of volume, right? Otherwise you'd be destroying matter. That is a very special point in chemistry, known as absolute zero. Absolute zero has a specific temperature. We'll talk about that in a minute. Charles observed that at a constant pressure, the graph of gas volume versus temperature yields a straight line. You'll also notice that at a certain point, when the gas gets to a certain temperature, the gas will have zero volume? That's really strange. Now, someone caught on to this. William Thomson was also known as Lord Kelvin. He became a lord, he lived in England, you get knighted and called Lord Kelvin. He took a look at the information that Charles published, and he found in his data this particular point could be theoretically thought of, that no one would be able to get that material that cold. So he attempted to get cooler and cooler and cooler, but unfortunately the technology of his time kind of limited him. So what is this absolute zero thing about? It actually has a very specific temperature. It's a temperature at which you drop down to negative 273.15 degrees Celsius. Trust me, eventually you're going to memorize this number. This is the temperature at which the kinetic energy of all the particles inside the container is zero. In other words, no temperature. If you had no temperature, that means that you have absolutely no kinetic energy, which means the electrons are not spinning around the protons, which means if that doesn't happen, oh my gosh, the electrons are going to spin spiraling into the middle of the center of the nucleus, and oh my gosh, you just destroyed matter. That's just not possible. You can't have gas have zero energy or have zero volume. Now, remember how I told you I'd tell you how to calculate kelvins? Well, kelvins, the unit kelvins, came from, you guessed it, Lord Kelvin. Kelvin is another unit of temperature, and you can determine Kelvin by taking your degrees Celsius and adding 273.15 to that number. This is a really important formula. Make sure you write it down. Charles's law, a little bit more. The volume of a fixed mass of gas is directly proportional to its Kelvin temperature if the pressure is kept constant. Since there is a direct relationship, then you can write Charles's law as follows. So this is Charles's law. V1 over T1 is equal to V2 over T2. Now there's a couple stipulations. Make sure that you always keep your volume in liters only. Make sure you also keep your temperature in Kelvin only. Very strict guidelines when you use Charles's law. Now, of course, I want to show you a quick example. And there you had a good example of this particular law. So here's a real example. If a sample of gas occupies 6.80 liters at 320 degrees Celsius, what will be its volume at 25 degrees Celsius if the pressure does not change? So you'll notice that I made you a little mental note that you can't use degrees Celsius. All right, you have to have your degrees Celsius changed into Kelvin. So again, the formula for changing your degrees to Kelvin looks like this. It's degrees Celsius plus 273.15. So this is the point where you're going to want to grab your calculators. I plugged in some information for you already. This is 6.8 liters. Probably you should go with this particular temperature, 320 degrees Celsius. Don't forget to convert that to Kelvin. After you convert this temperature to Kelvin, this belongs with your V1, which is right here. Okay, this is V1, this is T1, so these belong together. Now on the other side, we're being asked what will be its new volume, and this temperature right here you're going to have to convert to degrees Celsius, and this temperature you're going to stick on the denominator on this side. So take a minute, grab your calculator, and solve this problem. There's one more gas law that we need to study before we're done. Alright, so I'm just kind of curious what you're thinking in your head when you try to pronounce this gas law. It's actually Guy-Lussac's. Okay, Guy-Lussac's is how you pronounce it. So this particular gas law involves the temperature-pressure relationship. So think about those little balloons that you saw on the video that you just saw on YouTube. So when you drop temperature, think about the motion of the gas particles inside. If you drop temperature, you're also going to have the same direct relationship with pressure. It's also going to drop. So remember your definitions. Inverse relationships means that when one goes up, the other one goes down. Direct relationships mean that when one goes up, the other one goes up. And when one goes down, the other one goes down. Well, Guy-Lussac's is another direct relationship, just like Charles. The only gas law that has an inverse relationship was Boyle's law. Alright, please make note that when you use this gas law, you have to make sure that the pressure on both sides are in the same unit and that you convert your temperature to Kelvin. It's really important that you remember that. Now, when you combine all of the three gas laws that I just taught you, you come up with a new one called the combined gas law. Well, technically speaking, this is, if you think about it, this is all of the three gas laws. Now, I mentioned before in some of the earlier slides that you had to hold certain stuff constant. So if I hold temperature constant where T1 and T2 are exactly the same, which means technically, mathematically, you can cancel them, look at what gas law you have right here. P1 V1 is equal to P2 V2. Doesn't that sound like Charles's gas law? Now, what if I hold volume constant? So volume is held absolutely constant. Whose gas law is this? P1 over T1 is equal to P2 over T2. This is the relationship between pressure and temperature. Whose gas law is this one? And then finally, what if I hold pressure constant? And now all you have left is V1 over T1 is equal to V2 over T2. Whose gas law is this? So as you can see, all of these gas laws can be expressed with one simple combined gas law. Just remember one thing. Just remember one thing. The only variable that is on the denominator of this fraction is temperature. Now, we haven't discussed one relationship that I showed you at the very beginning of the slide. Do you remember when it looked like a kind of like a tire pump and you were pumping in more gas particles inside of a container? Well, that does cause an increase in the pressure, right? Well, where is the amount of particles in here? I don't see it in this formula. We need a variable that represents the number of particles inside of the container. It is one more variable, N, moles. So we do need to incorporate moles into the problem. The question is, where should it go? I don't know if you've recognized a trend yet with all of the math. So let's think about the relationships here. With Boyle's law, you had an inverse relationship, and that was a multiplication between pressure and volume. In Charles's law, you had a direct relationship, which meant that the formula had one variable on the denominator, and you were dividing in there. And then if you look at Gay-Lussac's, you also had a direct relationship, and the formula had some division involved. Are you starting to see a trend? Anytime you have a direct relationship, that would be corresponding to some kind of division. Any time you have a direct relationship, that is involved with some kind of multiplication. So let's see if you can predict where n should go. Okay. Now, if I increase the number of particles, I am going to increase pressure. Think about that. Like if you have a flat tire, you got to increase the amount of gas particles inside of your flat tire. Oh my gosh, okay, so if you're increasing the number of particles, which is moles, and you're seeing an increase in pressure, that's a direct relationship. Anytime you have a direct relationship, that should mean some kind of division. They should be, like one should be on the numerator and the other one should be on the denominator. So you already know where pressure goes. Pressure is on the numerator. Well, n would have to be on the denominator. I think you just solved it. This is also the combined gas law, but we just incorporated one more variable. These are all the variables that I introduced to you at the beginning of this PowerPoint when I was talking about all the variables that we talk about with gas laws. This is the official combined gas law. Sometimes scientists like to simplify it by just talking about pressure, volume, and temperature. But in reality, we really need to make sure that we are talking about n as well, just in case we have gas particles leaking into the system or somehow leaking out of the system. Alright, so remember when I talked about the piston and, you know, the gas particles inside could never escape outside? Well, what if they could? You know, what if we could introduce more gas inside the system while it's going through a change? That's possible, and so that's why this gas law is needed.
This is a really fun demonstration that can easily be done as a student activities. Students love to do this as an activity. It provides an effective introduction to atmospheric pressure. To get started, you'll need some pop cans. You'll need a striker and a Bunsen burner, a little bit of water, some tongs, and a large container of cool water. Pour about 20 milliliters of water into the can, get the burner started, and then hold the can over the burner to cause the water to boil. The purpose of the water is we want the water to change to steam, and that forces the air out of the can. You'll know that it's ready to go as soon as you see the fog or the cloud form outside the opening of the can. Then in one smooth motion, invert the can into the cool water.
That's the end of the lecture.